Hi everyone, in this video I'm going to look at graphs of the derivative function. So basically what we have to be able to do is we have to be able to look at a graph of something and we have to be able to decide on what the graph of the derivative should look like. Now with all the differentiating we've already done, we've seen that as we differentiate things the powers decrease. So x cubed becomes x squared and x squared becomes x and x becomes just a constant, x to the 0. And likewise x to the negative 1 becomes x to the negative 2 and so on. Okay, now what this means is that if we have a cubic function to start off with, then the derivative of it should look like a quadratic. And likewise, if we have a quadratic to begin with, the derivative of it should look linear. And if we have a linear to begin with, then the derivative should be a constant. Okay, the graph of a constant would just be a horizontal line. And if we had the graph of a hyperbola to begin with, the graph of the derivative should be the graph of a truncus. Now, let's have a quick look at the questions here. So sketch the graph of the derivative. Okay, this is a straight line, or it's meant to be straight anyway, and looks like it has a gradient of 3 based on the fact that we've got a rise of 3 and a run of 1. So I know from this that m is equal to 3, and remember m is the gradient, which is the derivative. So for this entire graph, forever in both directions, it will always have a gradient of 3. And so I'm just going to draw the line as a constant value of 3. There it is. That line has equation y equals 3. Now, what I'll say about this is that it's not at all a precise method. Like, this is something which is done fairly roughly. But yeah, that's something that I'd say method students often have trouble getting their heads around. In this one here we have a negative cubic function, so the derivative should be a negative quadratic. It doesn't matter what the equation is. I can see there are 2 points where it has a gradient of 0. It has a gradient of 0 at x is negative 2 and at x is 1. So at those 2 places it's going to have a gradient of 0, which means that on the graph of the derivative it'll have an x-intercept. So at negative 2 and at positive 1. Those are both x-intercepts. This has to become a negative quadratic, so it should be going up through here and down through there. And you know what we can see is if we look at this, to start off with up here somewhere it's going to have a very negative gradient. So very negative down there. And as we get close to the turning point it's only a little bit negative, so just a little bit negative there. And then it goes positive and it becomes steeper and then it becomes flatter again. So the gradient increases and then it decreases again and we'll go back down here. And then the gradient goes a little bit negative and then it goes more negative and then it goes very negative. So it's going to trace down like that. So lastly, I just try to sketch it as best I can, going roughly through those points. There we are, that was one. Right, so looking at the third one, this is also a cubic function, but in this case the cubic doesn't have any stationary points, so this is something that happens every now and then. It's quite unusual to see this, I guess. You know, we usually expect them to have turning points, but what we can see is this is a cubic where the gradient is always positive. So it's got a very, and we know that a cubic becomes a quadratic. This is also positive, so it'll be a positive quadratic when we differentiate it, but it's got a very positive gradient. And then the gradient becomes less, but it's still positive. So, you know, gradient's becoming less and less. It's always going to be positive though. And then the gradient becomes steeper again, so it starts to go back up. So based on that, I can draw that quadratic. And the last one is a modulus function. Now, looking at this, we've got a run of 2 and a rise of 5. So the gradient to start off with on this left-hand side is 5 over 2. And that will just be a constant. So it goes along and it has an open circle there because it can't be differentiated there. Likewise, the gradient here would be negative 5 over 2, so open circle and on out that way. Bit of a weird looking one, but we'll leave it for another day. Anyway, see you later.